In this video, we will present an overview of the Michelson language and the principles of a stack language. Michelson is a smart contract language designed specifically for Tezos. It's the only language that is running directly on the Tezos blockchain. All the other languages generate Michelson. As it's a low-level language, it's a bit hard to understand, although it's readable. You can think about it as an assembly language for the Tezos blockchain. There are no variables. Everything is based on the use of a stack. On the other hand, it offers some advanced features, such as a static type system with a number of basic types, built-in data structures, such as pairs, lists, maps, sets, and big maps, and an API to access the Tezos protocol, like crypto curves, transactions, etc. Michelson is a stack language. What does it mean? Imagine a stack of plates where each plate holds a value. Most instructions in Michelson affect a number of values at the top of this stack. Some instructions can reach beyond the top of the stack, but it's always relative to the top of the stack. So for example, to compute 3 plus 4 times 5, we'll write this program. First, we push the three values, 3, 4, and 5, on top of the stack. Then we use the instruction mul, which consumes 4 and 5 from the top of the stack and puts the result of the multiplication of these two values, 20, on top of the stack. Then we call add, which consumes 20 and 3 from the top of the stack and puts 23 on the stack. So at the end, we end up with only one number, 23, on the stack. So when programming this way, the harder aspect of a stack language is to keep the content of the stack in your mind after each instruction. Thankfully, there is a number of tools that can help us with this. So first, let's see a few examples of instructions in Michelson. One we have already seen is push, followed by a type and a value. This places a given value of a given type on top of the stack. Then we have dup, which pushes a copy of the value that is currently at the top of the stack. So it duplicates the top of the stack. Drop consumes the value of the top of the stack and doesn't do anything with it, so it just removes it from the top of the stack. Dig and a position removes the value at the position pause places from the top. So for example, dig2 will remove the second place from the top and then pushes it to the top. It moves it from its original position to the top of the stack. Add consumes the top two numbers from the stack and pushes their sum. Mul does the same thing for the product. Then we have operations on pairs. So unpair consumes a pair from the top of the stack and pushes its two different values separately. And pair does the opposite. It consumes two values from the top of the stack and pushes them as a pair. Finally, nil and a type pushes an empty list of elements of the given type on top of the stack. Here is an example of smart contract in Michelson. Like every smart contract, it takes a storage and a parameter, and it will produce a new version of this storage and a list of operations. So this specific smart contract takes as a parameter a pair of integers, let's call them a and b, and it computes 2a plus b. And finally, it stores the result in the storage. So basically by producing a pair that contains an empty list of operations and that result. So if we open this contract in Gitpod in our VS Code environment, we have some extensions installed that help us understand what's going on. So for example, anytime we click on one instruction, we can see on the right side what are the types of the elements on the stack before and after this instruction. So for example, here we push an integer, we see that there's now 3 elements on top of the stack. So the top one is here and the bottom one here. Then we multiply them, then we go from 3 integers to 2 integers. And at the end, in the last instruction, we create a pair composed of a list of operations and an integer. And when we start with a pair composed of a pair called parameter of ints, and the other element of the first pair is an integer, which is the storage. We can also debug this program by clicking on this button and then here, and we can provide the parameter for the contract. So let's say we need a pair of ints, so we can write the pair of int between parentheses. So let's say we want to have a equals 4 and b equals 5. So let's type this and press enter. Then it asks us for the initial value of the storage. And since we just want to store the result of the computation in storage, it doesn't really matter, but we can put 0 in the storage initially. Then we start with debugging step by step. On the right side, we still see for the current instruction the type of the content of the stack before and after the execution of this instruction. And on the left, we can see the content of the stack before the execution of the instruction. So you can see here, we have a pair composed of our parameter, the pair 4 and 5, and then the initial value of our storage. And we can click on this button to execute the current instruction. So the first instruction is unpair. And what it does is it splits those two elements and puts them separately on the stack. So now at the top of the stack, we have our parameter and then the storage. Now we can do unpair on the storage itself. And so now we have A on top of the stack, B, and then the storage. So you can see what we did here is in the comments. To help make it easier to read, we copy basically the description of what is on the stack at this time. So on this time, we have A at the top of the stack, then B, then the storage. Now, if we do dig2, we will take the element at position 2 from the top. So this is this one, 0, 1, 2, and we'll bring it to the top. Here you can see that 0 was brought to the top. Then we drop this 0, we get rid of it, it disappears, and then we do dig1, so we get the element at position 1 and bring it to the top. Then we push 2. Then we multiply 2 with the second element from on top of the stack, which is B. And so we get 2B at the top of the stack. Then we can add those two elements, so we get the result, 14, at the top of the stack. Now, as for every contract, we need to return a list of operations in a pair with this list of operations and the new value of the storage. So we push an empty list of operations to the top of the stack, and then we create a pair with those two. And that's it. We have the output of the contract, which is this empty list of operations and the result of the computation. And now it will be your turn to write a small and similar smart contract.